All right, so water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. If the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? All right, so let's draw our picture here. All right, so our cylindrical tank. Notice the water is leaking. All right, so leaking means the derivative is going to be negative. All right, so if the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? Let's identify all our variables. All right, so we have, well, we are dealing with, so if we have something flowing out of a tank, that's volume. We have the radius, and h is the height. And we're interested when the radius is 4 feet. Now identify which, if any, of the variables in the problem remain constant. Right? Well, the water is not going to all bunch up on one side of the tank. So the radius is a constant. So I don't think I put 4 feet up there. 4 feet is the radius of the tank throughout the problem, right? The radius doesn't change. This isn't, the walls of the tank aren't coming in or, moving out, right? That tank has always had a radius of 4 feet, so that's going to be a constant. So we can just use 4 for radius. And actually, let's just move that right down there. Identify the rates that are given and the rate you wish to find. All right, so we are at what, so if we look, we are given the water leaking out of the tank, that's dV dt. Right, and since it's leaking, it's negative 3 feet cube, 3 feet cube per second. We want, so at what rate is the depth of the water changing at any instant during the leak? We are looking for dH dt. We want to know how the height of the water is changing. That's what we want to find out. All right, so writing an equation, we're dealing with volume of a cylinder. We should use the volume of a cylinder as our equation. All right, so we have V equals pi r squared, the area of a circle, times the height of the cylinder. The radius, however, isn't changing. So we can replace the r, right? So substitute any value that represents a variable that is constant throughout the problem. So that's the only ones we're allowed to change. Right? So we have from a variable to a number value until we take the derivative. So V equals pi times 4 squared times h. So that's just V equals 16 pi h. Right? So 16 pi is just a coefficient. Now let's take the derivative with respect to time. dV dt equals 16 pi dH dt. Right? Because the coefficient will remain, and the derivative of h with respect to time is dH dt. Right? So we want to solve for dV dt. Let's isolate, dH dt. Let's isolate dH dt. Right? So this part here was 4, and This part here is 5. It wasn't too hard to take the derivative on that one. And then now we're going to isolate. So now this is 6. We're going to isolate and solve. So we have dv dt divided by 16 pi equals dh dt. Now let's just plug in our values. So dv dt was negative 3. We don't need the units. We'll put the units when we finish. Negative 3. And that's it. 16 pi divided by 16 pi is dh dt. Guess what? That's it. We're done. Nothing more to simplify. All right, except we need to put the units, and then we'll explain what that means. So dh dt, this is a linear unit, would be negative 3 over 16 pi, and this is feet per second. So volume is feet cubed, and the height is just feet. So that means the water level is decreasing at a rate of negative 3 divided by 16 pi feet per second. And it actually doesn't matter when this happens, right? Because no matter what, the radius is 4 feet. But let's put that in, because if we had a different tank, then this would be a different problem. So we'll put in when the radius is 4 feet. Of course, in this problem, the radius is always 4 feet. All right, so we have solved for the rate of decrease in the water level. And so come back and we'll do another one. Thanks for watching. Bye for now.